All the Python source code for this lesson is available for download. See video description. Welcome to our guide on Convolutional Neural Networks, CNN, image classification. See CNN Lesson 1 for the introduction to CNN. Here we will start from understanding convolution. The concept of convolution. Convolution is a mathematical operation that forms the backbone of a convolutional neural network. In the context of a CNN, convolution involves taking a filter, also known as a kernel, and sliding it over the input image to produce a feature map or convolved feature. This operation allows the network to learn and identify spatial hierarchies or patterns in the input data. The role of filters. Filters in a CNN are small matrices of weights which are learned during the training process. Each filter is designed to detect a specific feature in the input data, such as edges, corners, or more complex shapes in higher layers of the network. The size of the filters is a key parameter in a CNN and is usually chosen based on the complexity of the input data and the level of detail required in the feature maps. Performing convolution. To perform convolution, the filter is slid over the input image and at each position. A dot product is computed between the filter and the part of the image it is currently on. This results in a single value that represents the presence of the feature the filter is designed to detect. The process is repeated for every position on the input image, resulting in a feature map that represents where and to what extent the feature appears in the image. Stride and padding. Stride and padding are two important concepts in convolution. The stride refers to the number of pixels by which the filter is shifted at each step of the convolution process. Padding involves adding extra pixels around the input image to ensure that the filter fits properly at the edges. Both stride and padding can be adjusted to control the size of the output feature maps and the level of detail they capture. The power of convolution. Convolution allows a CNN to learn complex patterns in the input data using relatively few parameters. By sharing weights across the input, the network can recognize the same feature, regardless of its position in the image, giving CNNs their characteristic property of translation invariance. This makes CNNs particularly effective for tasks involving images, where the same feature can appear in different positions. The architecture of a CNN. A typical convolutional neural network consists of an input layer, multiple hidden layers, and an output layer. The hidden layers often include a series of convolutional layers, followed by activation functions, pooling layers, fully connected layers, and normalization layers. Each of these layers plays a specific role in the processing and transformation of input data. Convolutional layers. Convolutional layers are the core building blocks of a CNN. They perform a convolution operation on the input data and pass the result to the next layer. The purpose of the convolutional layers is to extract high-level features from the input data, such as edges, corners, and other relevant attributes. Activation functions. Following each convolutional layer, an activation function is applied to introduce non-linearity into the model. This allows the network to learn complex patterns and relationships in the data. Commonly used activation functions in CNNs include the rectified linear unit, ReLU, sigmoid, and hyperbolic tangent, tanh. Pooling layers. Pooling layers are used to reduce the spatial dimensions, width and height, of the input volume. This serves to decrease the computational complexity, control overfitting, and consolidate the features extracted by the convolutional layers. Two common types of pooling are max pooling and average pooling. Fully connected layers. Fully connected layers connect every neuron in one layer to every neuron in the next layer. In a CNN, fully connected layers often come after several convolutional and pooling layers, and they serve to interpret the features extracted by the convolutional part of the network. The final fully connected layer uses a softmax activation function to output a probability distribution over the classes. Normalization layers. Normalization layers, such as batch normalization and local response normalization, LRN, are used to standardize the inputs to a layer for each mini-batch. This has the effect of stabilizing the learning process and dramatically reducing the number of training epochs required to train deep networks. The combination of these layers forms a CNN architecture. The exact architecture can vary widely depending on the specific application. But all CNNs follow the general pattern of alternating convolutional layers, with activation functions and pooling layers, followed by fully connected layers. All the Python source code for this lesson is available for download. See video description.